So now that we've recapped what the electric field for a point charge is, let's look at a situation where there's more than one point charge. Let's take an electric dipole, which is any situation where you've got equal and opposite charge spaced some short distance apart, s. So let's say you've got one of these electric dipoles and you want to know, hey, over here at x, what's the electric field like? There's an electric field from the positive Q, there's an electric field from the negative Q. We just need to find both of those electric fields and add them. The negative Q creates an electric field that points towards it, and then that positive Q is going to make an electric field that points away, and it's going to be larger because where we've drawn this picture, you're slightly closer to the positive charge. The overall electric field that you feel at x should just be those two electric fields added together. I'm going to stick a negative in front of that second electric field because if you look at the picture, that vector points in the negative direction. Each of these electric fields are being created by point charges, so we can just use that equation we had before for electric field. So from the positive charge, kq over the distance from x to the positive charge. If we look at that, that's just going to be x minus s over 2. So that distance squared, and then for the negative charge, same difference, except it's a little further away by s amount. There is something educational to be gained by simplifying it further. So I'm going to combine these two into one big ass fraction. If I factor out this kq, I've got 1 over x minus s over 2 squared minus 1 over x plus s over 2 squared. I'm going to put them over a common denominator, x minus s over 2 squared, x plus s over 2 squared. And then on the top, you got to multiply those denominators across. So we can expand the stuff on top. So if I just put this stuff out here, that stuff on top, this bit here, you can double check this if you like. I'm going to save us some time. It's going to simplify down to 2xs. So now it's an important moment to note that if you have a dipole, if you have, for example, a water molecule, the two ends of the dipole are very close together compared to any place that you're going to stick an electric field probe to measure electric field strength. So that distance x is always going to be way, way bigger than the separation of those charges. So x is always much, much bigger than s. That means that x minus s over 2 squared, and the dipole moment is defined, an equal sign with 3 bars means defined, as q times s. And q is just the charge of one of those charges, not both of them, because they're supposed to be equal and opposite charges with a dipole. So the charge times the space between the two charges. So the electric field for a dipole, and in this case specifically when you're looking along the axis of the dipole, is 2k times the dipole moment over x cubed. This is actually kind of interesting. For a single charge, the electric field gets weaker as 1 over x squared as you get further away. But a dipole, the electric field actually falls off much faster because you got two opposite charges close together. Far away, they should just look neutral. So this dipole falls off much faster. So we just looked at the electric field on axis for a dipole. Let's do something slightly different and look at the electric field on the axis bisecting the dipole. So let's say you're some distance y away from the center of this dipole and you want to figure out, hey, what's the electric field? So you're going to get some electric field from this positive charge pointing this way. And you're going to get some electric field from this negative charge pointing this way. And you can see from this picture that the y components of these two are going to cancel, and you're just going to be left with net electric field in the x direction. So in this case, that net electric field, that's just going to be the positive charges electric field, the negative charges electric field, but just the x component. And since these are equal in strength, we could write that as kq over, let's see, this distance right here is s over 2 squared plus y squared, square rooted. So then if we square it again to put it on the bottom, s over 2 squared plus y squared. But we only want the x component of that. So this electric field here, it's two x components, one from each of these electric fields. We just want the x component of that. So there's some angle here, theta, and that's the same angle as right here. So this x component of electric field is related to the overall magnitude of the electric field via that angle theta. Specifically, it's a sine component. So if you want to find the net electric field here, we're going to have to do kq over s over 2 squared plus y squared times the sine of theta. Okay, so you guys need to finish this up for Canvas. I did a lot of the steps. What I'd like you to do now is to get rid of this component and put this in terms of y's and s's. So step 1, put it in terms of y's and s's. Step 2, recall that dipole moment is q times s, so you should be able to make that substitution somewhere. And step 3, simplify for the case where y is way, way bigger than s, as is typical for a dipole. So do these steps, and then enter that big-ass formula for electric field into Canvas.